welcome to Simplified Physics. In the previous lecture of dimensional analysis, we have discussed about the applications of the dimensional analysis. In this lecture, we will discuss some more application about the dimensional analysis. In the previous lecture, we have discussed the first application as to check the correctness of the physical relation. Second application, determination of the dimension of the constants in the physical relation. Now further we discussed the third application, deducing the physical relation among the physical quantities. In order to derive a physical relation among the physical quantities, we must know about the dependence of the particular physical quantity with the other physical quantities, and another essential point is the relation must be, or dependence must be, the product type. In such condition we can derive physical relation. Let's see an example. How can we derive the time period of a simple pendulum using dimensional analysis? Let's begin through the definition of the simple pendulum. What is a simple pendulum? In fact, a simple pendulum has a bob attached to a string which oscillates under the action of the gravity. So on the basis of this definition, we have some ideas about the time period. Time period may depend on the effective length of the pendulum, mass of the bob, and acceleration due to gravity. So we may write as time period is directly proportional to length of the pendulum, but we are not sure about the factor, on what factor it depends. So L power A, where A is a number or simply a constant, dimensionless constant. T is proportional to mass as well. We assume that may depend on the mass, so it is proportional to m power B. B is a unknown number. Similarly, time period may depend on the acceleration due to gravity. So just combine this relation, we'll get a T proportional to L power A, m power B, G power C, and further we may write as T equals to K, L power A, m power B, and G power C. Let us suppose it has equation 1. In equation 1, K is a dimensionless constant. A, B, C are simply the numbers. Now our aim is to find the values of A, B, and C. Let's begin. Now write the equation, equation 1 in terms of the dimension. So in terms of the dimension, we may write for the time has a dimension T, length has the dimension L, and its power as it is. Similarly, m, that is the mass, has the dimension m, and the acceleration due to gravity has the dimension Lt minus 2. So we can write as T equals to L power A, m power B, Lt minus 2 whole power C. And in general we may write in term of MLT as in the form of m power 0 L0 T1 equals to, look at the right hand side, m has the power B only, L has the power A from the this term, and from the Lt minus 2 L has the power C, so L power A plus C, and about the T minus 2C. Now on the basis of the principle of homogeneity of the dimensions on the both sides must be identical, then only the given relation we can say dimensionally correct. So all the terms on the physical relation must have the same dimension. So just compare the dimension, equating the dimensions of each term. Mass has dimension 0, that means B equals to 0. Similarly, A plus C equals to 0, dimension of the L. Similarly, dimension on the time has minus 2C equals to 1. B equals to 0, that's obvious, B equals to 0 from the first. What about the C? C equals to minus 1 by 2. Now using the values of C in equation A plus C equals to 0, we will get value of A as 1 by 2. Now putting these values A, B, and C in equation 1, we get the equation. We can rewrite the equation 1 as t equals to k l power half m power 0 g power minus half, or we can write m power 0 means simply 1, whatever the number or quantity. If it has a power 0, that's a 1 unit quantity, so remaining quantity t equals to k. L has the power half, g has the minus half, means we can write as L by z 1 by 2, 1 by half g, or simply L by z. We get the equation 2. We are almost close to the time period for the simple pendulum. K already mentioned that k is a dimensionless quantity. We cannot find the value of k using the dimensional analysis because it has no particular dimension. It can be found, the value of k can be found mathematically as k equals to 2 pi. Thus we can write the time period of a simple pendulum as t equals to 2 pi square root of L by g. This gives the time period of a simple pendulum. In this way we can determine the physical relation on the basis of dimensional analysis. Dimensional analysis can be used to find the relation between the quantities when the mathematical analysis is too difficult. This means if the mathematical analysis is not comfortable finding the physical relation, we use dimensional analysis, and the relation or dependence must be product type already mentioned, and we must have an idea on which factor, on which physical quantity the given physical quantity may depend. Now let's go for the fourth application of the dimensional analysis. We can convert the one system of units to the another system of unit using the dimensional analysis. The dimension of the physical quantity remains the same irrespective of the system of measurement. That means whether we choose the CGS system, SI system, FES system, it doesn't matter. The dimension for the particular physical quantity must be same. For example, dimension of a velocity will be always LT minus 1, whether you use the CGS system, the unit as a cm per second, or SI system as a meter per second, doesn't matter. It depends on the physical quantity. That means simply the physical quantity has the same dimension. It doesn't depend on the choice of system of unit. Let us suppose, let's go for the example. Suppose we have a physical quantity Q. Now choose the two system of unit for the given physical quantity. U1 and U2 be the units, units in the two different system, and UN1 and UN2 be the numerical values of the physical quantity in the two different system. If the system of units are different for a given physical quantities, units are different, numerical values are different. For example, length of a particular substance is 10 centimeter. 10 centimeter means in CGS system numerical value n is 10 unit centimeter, but in SI it's 0.1 meter. That means numerical value also different from the system, and unit meter, that is also different from the CGS system. That means numerical values and units are different. What about the dimension? Dimension always remains same for a particular physical quantity. That is, we have chosen as a length has always the dimension L. So if we have chosen the two different system, units are in general different, maybe same in some cases. For example, in case of time, whatever you choose, CGS or SI, unit is same. So in general the units may be different in different system of unit. So let's suppose U1 and U2 be the units in two different systems for a same physical quantity, and n1 and n2 be the numerical values of a physical quantity in two different systems, and a physical quantity, let's suppose q. Then we may write the physical quantity q equals to n1 into u1. n1 numerical value, u1 unit for the first system of units, so q equals to n1 and n2. Similarly, in the second system we can write q equals to n2 into u2. In the second system, that is numerical value times unit. Then in general, q equals to n1 u1 equals to n2 u2, because the value in the one system of unit is same as second system of unit. That means simply 10 centimeter equals to 0.1 meter, they are equal. So we can write q equals to n1 u1 equals to n2 u2. What about the dimension? Let us suppose the given physical quantity has dimension m power a, l power b, t power c. We have no idea about the abc because it's not a specific physical quantity. It can be any physical quantity. We just suppose in terms of m, l and t as m power a, l power b and t power c. So let's suppose a given physical quantity q has the dimension ma, lb, tc. Then in the first system of unit, m1, l1 and t1 be the base units on the first system, and m2, l2 and t2 be the base units in the second system. So we may write the equation 1 as q equals to q as it is of physical quantity n1 is a numerical value, it has no dimension. So in the first unit u1 in terms of the base units as m1 power a, l1 power b, t1 power c. Similarly, n2 is a dimensionless numerical value, n2 as it is. And in terms of the second system of unit, for the second system of unit, the base units are m2, l2 and t2, so we can write m2a, l2b and t2c for the dimension after given physical quantity in the second system of unit. So we may write equation 1 as q equals to n1 m1 power a, l1 power b, t1 power c equals to n2 as n2, m2a, l2b and t2c. Simplified equation, if we are converting from first system of unit to second system of unit, we can write numerical value for the second system of unit n2 equals to n1. Now just divide m1 by m2 power same, l1 by l2 power b and t1 by t2 power c. Using this equation we can convert a physical quantity in one system into another system of unit. Let's see an example. Let's convert 10 power 7 ox into joule, and we are familiar to the unit joule and ox. Joule and ox are SI and CGS units of the work. Ox and joules are, ox is a CGS unit and joule is a SI unit of the work. And what about the dimensions of the work done? Dimension of the work done is ml to t minus 2. So if you are confused with the dimension, let's go from the relation work done equals to force into displacement. Force has the dimension ml t minus 1. Is it? No. ml t minus 2. Force has the dimension, and yes is a displacement has one more, gives the one more L. So we can write dimension of the work done is ml2 t minus 2. And in general we may write ma, lb, t power c. If we equate to this relation the dimensions of the m as 1, l as 2 and t as minus 2 in the work, dimension of the work, so a equals to simply 1, b equals to 2 and c equals to -2. Now let's go. We have to convert from ox to joule. That means CGS system to the new system, that is SI system. The given system has n1 equals to 10 power 7 ox. N1 is given, 10 n1 equals to numerical value n power 10 power 7. N2 we have no idea, we have to find n2. Now in the units, m1 in CGS equals to 1 gram and m2 1 kg in a unit. Similarly, for a unit length is 1 centimeter in CGS and 1 meter in SI. Similarly, unit time is 1 second in CGS and 1 second in SI as well. Now use this for relation n2 equals to n1, m1 by m2 power a, l1 by l2 power b, and t1 by t2 power c. Just replace the values. n1 equals to 10 power 7, m1 equals to 1 gram, 1 by 1 kg, m2 equals to m kg, and so on. We have replaced. Now s and s cancel, and power, so this value is simply, last term I am looking for 1 power minus 2 means simply 1. Whatever the power for the 1, it's simply gives to 1. Now 1 gram and 1 kg we can't cancel. Either convert 1 gram into kg or 1 kg into gram so that we can cancel. Okay, what I have done for this, I have converted 1 kg into gram, so gram and gram cancels. Similarly, 1 meter into centimeter, here c is missing here, centimeter, in fact c is missing, so centimeter cancel, so 3 zeros, 10 power 3 zero cancels, 10 power 4 left. Now here is square of this, that means 100 square means 10 power 4 simply cancels 10 power 4 as well, so we'll get n2 equals to 1. So 10 power 7 ox into 1 joule. Can you convert 1 joule into ox in a similar way? Just a difference will be, starts from here, SI, the given system will be SI and new system will be CGS. The variation will be, it's a 1 joule and we have to find n2, and it will be 1 kg, 1 meter, 1 gram, 1 centimeter, and just replace the values. No matters whether you are converting from CGS to SI or SI to CGS, it doesn't matter. You can convert 1 gram into kg or kg into gram. What if we have changed gram into kilogram? It's a 1 by 1000 kg. Kg cancel. The same result you will get. So it doesn't matter. Just in similar way, any conversion you can do if that in fact depends on mass, length, and time. And this is the end of today's lecture. Thanks for watching. Any questions and suggestions you may forward to this email address. Thanks for watching.